keyboard on this computer. All right. Good evening. Happy Tuesday. This class probably isn't going to be super long because number one, we just had a test and Thursday was a lot of material. So those are my two things. We just had a test and kind of need a little bit of an easy going on our class. Plus, I went through a lot of material on Thursday. So I'm trying to keep it lower key. Hoping you are all happy about canceling lab 4. I don't think that broke anybody's hearts. So, didn't break my heart either. It's not my favorite lab.
Thank you.
You're welcome. You're welcome. It's not my favorite of the labs. My favorite of the labs, the linear regression one is super useful later on, and I love the descriptive statistics because I like that it shows everything all in one spot. Both of those things are super useful when you do your final project. I highly recommend send in your project proposals. Even if you don't care about the extra credit, if you're sitting there with like 98% in the class, which I don't know whether or not anybody is, I don't keep super close tabs on that, but you might be sitting there with a really strong A and be like, you know what, I'm cool, I'm fine, just gonna sit here and glide and not give my project proposal. It gives me a chance to give you feedback. It gives me a chance to look at it and be like, whoa, this project is definitely not going to work. You may want to rethink some things, or say, this is fantastic, run with it the way it is, I love it. Or to be able to say, hey, if you want to make this a little bit richer, you might think about this as well. So I try to give feedback on every single one of those. Sometimes I'll have a conversation with somebody and we'll already kind of get feedback, but I'm going to at least write a comment and say, hey, we've already talked about this. This is great. You're good to go. So even if it's not fully fleshed out and you just say something about, I really like dogs and I want to look at weight of dogs and the number of bite attacks, something weird like that, and you're like not really sure what you're doing, just give me a quick sentence and say, here's what I'm interested, here's what I'm thinking. What do you think? It does
Yeah,
not have
because I don't know what to propose. Like, I don't know what it would be.
okay.
An idea for myself. I'm not sure if that's gonna work. I was thinking of doing a daily weigh-in and doing a working out for like an hour daily. Would
But
that be okay?
except for you're not going to have enough time to do 50 of those between now and
Oh,
turning
you
it.
need 50? Okay, thank
Yeah,
you.
because you
How
need
many things do you need? Just a one?
2 variables, 50 data values for each variable.
Thank you.
So yeah, read that carefully that I sent out. And it's also posted. There's a folder at the bottom of the assignments and lessons. Read through it and then come to me with any questions. Feel free to post a question about it in the forums because I'm sure somebody else has the same question. If you're not sure what you want to do this on, I'm not going to give a lot of ideas because this is your final project. This is like a final exam. I want the most of the braining to come from you. So think about, what am I going to be in school for? What is my major? What am I going to want to do? What career am I going to do after I graduate? Think about the things that might fit in with that career or anything else you're really interested in and you're passionate about. I've had people that have been like comic book collectors their whole lives and they'll do it on comic books. The best projects I've seen are the things that people do that they're passionate about. So just think about something that you are really passionate about and trying to think of some variables that have to do with that. A great place to just kind of peruse, to kind of get ideas, is like the census website. I think it's just like census.gov. It's a great place just to peruse and look at the different types of data they have. And sometimes something will jump out at you. Or, I'm not going to give you a whole lot of direction on what to choose because I want it to be about you, not about the ideas I give you. All right. And unless there's a really pressing question about that, I'd like to get on with today's stuff. Okay, so today we're going to talk about discrete and continuous random variables. Yes, we've already done discrete and continuous, but we're going to start applying it to more things. We're going to look at discrete probability distributions and their graphs. And we're going to look at a mean of discrete random variables. We're also going to talk about how you interpret that mean, and we're going to look at what expected value is. Then we're going to talk about the standard deviation of that discrete random variable. What we are doing right now is going to be applied to pretty much every chapter from here on out. Because even though we are only just almost halfway through I think we have about a week left before we're halfway through the term, or maybe it's the end of this week. I don't know. Anyway, we're more than halfway through the material. We go through chapter 10. We've already done 5 chapters. So we're in chapter 6. We are on the downward slope of the material. So strap in. Here we go. It's a fun ride. This stuff's fun, especially what we do with it later. Okay. I'm going to move on. Okay. A random variable. It is just a numerical measure of the outcomes of a probability experiment. So we use a capital letter X. And what I really don't understand is why in stats we choose a letter that looks almost exactly the same, capital and lowercase, and we decide to use that. And that's what we did here. A random variable is denoted as the capital letter X. So if I was rolling a dice and my outcomes are obviously 1 through 6, and I roll the dice and I want the 6 to be my success, then my random variable would be % of the time that I roll a 6, or how frequently I roll a 6, or whatever. So I'm going to show you some examples in a minute. I did start recording, didn't I? Yes, good. Okay, so a discrete random variable, it's the same thing as just a regular discrete variable. It has a finite or countable number of values. And most of the variables that we're going to be using from here on out are going to be discrete. We will have some continuous. Most of them are going to be discrete. So it can be plotted on a number line. There'll be spaces in between. If I graphed it, it would be dots rather than a solid line. Continuous, it has infinitely many values. It can be plotted in an uninterrupted fashion. It would be a solid line. You could draw it without lifting your pencil. This shouldn't be completely new information, and I just tested you on discrete and continuous. So hopefully we're good on this. So here's a couple examples of discrete or continuous random variables. So the number of light bulbs that burn out in a room of 10 light bulbs in the next year would be discrete because I can't have a partial light bulb burnout. The number of leaves on a randomly selected oak tree, that would be discrete because they're countable. Even though there's probably thousands and thousands of them, it's still countable, theoretically. The length of time between 911 calls would be continuous because it takes on every value in between 2 values. I can't hit 5 minutes between calls if I don't go 4 minutes and 58 seconds first. So it can take on every value in between. Questions? We good? So far, it's just review. So we've already also talked about a probability distribution, but this is going to, what's I going to say? I don't remember. So it provides all of the possible values of our random variable and the probability of each value happening. So remember, they all have to add up to 1. Altogether, they add up to 1. And the values have to be between 0 and 1. And we can use a table, a graph, or a formula. So here's an example of a probability distribution. Oh, and I just remembered there's a bad slide on here. We're going to kind of scooch on past the bad slide on here, so don't worry. I forgot to remove it when I was preparing for class today. So there's a bad slide on here. Anyway, so right here I have a probability distribution. If I added all those probabilities together, they would add up to 1. And in, I guess, this particular study, people streamed either 0, 1, 2, 3, 4, or 5 movies on Netflix each month. Apparently there's nobody that streams more than 5 movies, probably just for a specific sample. So if I randomly chose a person out of that sample or out of the population that we're studying, randomly chose a person, there's a 22% chance of choosing someone who streamed 2 movies that month. That's what this means. All right, I already mentioned this. For a probability distribution, a discrete probability distribution, all of the probabilities added together add up to 1. That's what this right here means. That means the sum of all probabilities is 1. That's a really ugly arrow. That's better. All of the probabilities add up to 1, and each probability is between 0 and 1. You're not going to get a probability of -4. If you do, you did something wrong. I had a student at the high school get a negative probability just the other day. It was pretty funny. He's like, Miss Kleiss, you taught this wrong. You taught this wrong because I did exactly what you did and I got a negative. I'm like, you didn't do exactly what I did. Trust me. He didn't. He didn't. He made mistakes. All right. So probability histogram, it is exactly the same as a relative frequency histogram. We just decide to recycle things and call them something different. So a probability histogram is the same thing as relative frequency, except we changed the title on the horizontal axis to probability. Everything's calculated the same way. It's plotted the same way. It's just named a different thing. Once again, we renamed things. So we're going to draw a probability histogram for the Netflix movies. Man, I can't speak. I apologize. So here's the histogram. Exactly the same thing as it would be if it was relative frequency. It just says probability on the side. Don't worry, I am not going to ask you to draw a probability histogram. I'm just showing you what it looks like. All right. So here's another lovely, lovely data set. We asked a basketball player to shoot free throws. He shot 3 of them, and we calculated how many times or how many shots he made each time. So he did quite a few trials of shooting 3 free throws. 3 free throws. So several times he did that. 38% of the time he made 2 of them. 51% of the time he made all 3 of them. So I'm going to show you another way that you can graph that probability distribution. It's not my favorite, but it's a nice way to draw a really quick graph. So rather than drawing the actual histogram, we just drew lines with little dots on the top so you can see how high it went. As I said, this isn't my favorite, but it is adequate. And I believe that there's one in our textbook that looks like this. We're going to do some math with these things. All right. So I'm going to talk about the mean and what it means. So when you are calculating the mean of a discrete random variable's probability distribution, I can't just add all the values and divide them by how many there are. The reason I can't do that is because each of them has a different probability of happening. If I just added them together and divided by how many there are, then they would have to have the equal probability. But this doesn't. So I have to make sure that they are weighted. In order to do that weighting, I have to, this is the formula, but let me show you how it works. I have to take each value, multiply it by its probability, and then add them all together. So I'm going to take 0. The probability of 0 happening is 0.06 plus 1 times 0.58 plus 2 times 0.22. And I'm realizing I wrote too big, so I'm just going to put it down here. Plus 3 times 0.10 plus 4 times 0.03 plus 5 times 0.01. Yes, I know technically I don't need the 0 on there, but I just do that so that I know I didn't forget anything. So in your calculator, you can put that entire thing. You can put all of those, put all of that math at once. 0, 0 times 0.06. It's 1 times 0.58. 2 times 0.22. 3 times 0.10. 4 times 0.03 plus 5 times 0.01. And I got, so my mean, mu sub x, it's approximately 1.49. So my mean is about 1.49. So the average number of videos streamed, or this is not Netflix data, but it's exactly the same as the Netflix data. I don't know why it changed. I got these slides from our curriculum. Our textbook provides these, and they changed it to DVDs. And I believe all these probabilities are the same. In fact, I'm going to pop back real quick. It's just really annoying to me. Yeah, they just changed the words in the middle of it. So the average number of videos a person rents from the video store rather than Netflix here is about 1.49. So if you randomly selected a person, you would expect that they rented approximately that. I know that's not a discrete value, but when you average things, we don't frequently get numbers that make sense. So you would expect the average number of videos a person rents is 1.49, so between 1 and 2. This is also called the expected value. We frequently see it written as this, and I'm going to change it here. We frequently see it written like this. You will be asked, in your homework, they will either ask you to calculate the mean, or they will ask you to calculate the expected value. These two things are exactly the same thing. Calculating the mean of the discrete random variable or calculating the expected value are exactly the same thing. So the expected value here is 1.49 videos. Questions before we do another one? I will show you how to do this on your calculator quicker, and it will make you happy. It will give you great happiness.
Yeah, this one is just like not divided by like 6, like we
No.
do on the regular mean, huh?
No, it's because we're multiplying it by the probabilities. We don't have to do the division.
Okay, thank you.
Yep, good question. All right, let's do it with the basketball player. Okay, look, it did all the math for me. Actually, let me, why, oh, why? I don't think we need this. Okay, we don't need that. All right, so this is basically your law of large numbers. So this is as we, the like meaning of the expected value. If I had super large number of trials, so I kept every person that went into the video store over and over and over, how many videos did you rent? How many videos did you rent? As I averaged those out, if I kept averaging those numbers, I kept adding all of those numbers together and averaging them out, the average would approach that expected value. That's what it means. The law of large numbers is that we would approach that. Let me give you a good example. So we have this globe in my classroom at the high school. When we start the probability unit in my stats class at the high school, I take this globe, which I assume when I buy it, that it is approximately 70% water. Every day we throw it around for the first 5 minutes of class. And everybody that catches it, they say whether their right thumb landed on water or land. And we keep tally marks on the board and keep calculating what percent of the time did our right thumb land on water. So the earth is approximately 70% water. This cheap globe beach ball that I bought, where we assume at the beginning it's about 70% water. When you first start throwing it around, the first few days, there's really wild varying numbers. We'll get 40% water one day, we'll get 80% water the next day. We keep going and going and going. As we toss the ball around and we end up with hundreds and hundreds and hundreds of trials, the amount of water answers we get gets closer and closer to whatever the actual percent of water is on that ball. And the ball that I have currently, actually, they just destroyed it because we got to the end of the unit. So they got very violent and it's dead now. But the actual value on that was about 66%. Now there's some error there, but since we had hundreds and hundreds and hundreds of trials, I'm guessing that the percent of water on that ball was probably pretty close to that 66%. Does that kind of help you with the expected value? All right, let's move on. Okay. Because the mean represents what we expect to happen in the long run, we call it the expected value. So casinos use expected value because they want you to think that you can win a game, but they want to be able to just barely be favored. So in order to do that, they would have to have an expected value of every dollar that comes in, and they want it to be in their favor. So they want it to be that they have less payout than they have coming in, or than they have less payout than they win. So they actually use expected value a lot. All right. Now we can do another one. I thought I was getting to the basketball already. I guess not. Okay. So a life insurance policy will pay a beneficiary a certain sum of money upon the death of the policyholder. These policies have premiums that must be paid annually. So a life insurance company sells a $250,000 one-year term life insurance policy to a 49-year-old female for $530. On here. So the probability that that female survives a year is this right here. So they get $530 from her at the beginning of the year, or broken into 12 pieces or whatever. And if she dies within the year, they have to pay out $250,000. So we want to know the expected value of this policy from the insurance company. So basically what we're looking for is if they sell many, many, many of these policies, and we always use many, many when it's a very, very large number of them. So many, many just means a whole bunch. They sell a whole bunch of these policies. In the end, we want to see, even if they pay some of them out, based on the probability, how much do they make from each policy in the long run with many, many policies sold. So if she survives, they make $530. And here's the probability she survives. If she does not survive, they lose $249,470. Here's the probability that she does not make it. So I take the probability that she survives along with the money that they make, then add it to multiply together. Then I take the amount of money they lose if she doesn't survive and multiply it by the probability she doesn't survive. So they would expect, even if they had to pay some of them out, they would expect that this is how much money they would make in the long run on each policy. Now, $77.50 doesn't seem like a lot, but if they're selling thousands upon thousands of these policies, $7.50 a policy is a lot of money. Questions? And I would probably bookmark this one or something, because I believe your next hand-in homework, not the one due today, but the next one has a problem very similar to this. So
What does What does the result represent, you said?
So they,
50?
the 750, so this insurance company sells a lot of these policies. We say many, many just to mean a really large number of these policies. Some of them they will have to pay out. Some of these 49-year-old women will die. They are expecting that based on these probabilities, they will make $7.50 per policy if they have to pay some of them out.
Thank you.
Yes, you're welcome. Anyone else? All right, I'm going to move on. I just did this one. Okay, I would like you to compute the expected value for number of free throws, doing exactly what we just did. After you do this by hand, we're going to jump back to Netflix data, and I'm going to show you how to do this on your calculator.
Melissa, did we already pass over the slide that you were going to delete or?
No, we have not hit that one yet.
Okay, thanks.
I will tell you when we get there.
Okay.
It's just there's some errors on it, and it was a slide that the textbook gave us, but I forgot to take it out. You get stuck, feel free to look up. I'm going to calculate it and then put the answer up there. So only look up if you're either done or stuck. Once you're there, let me know how you did.
Got it.
Yay!
Yep, got it.
Good. So what this is saying is that if he shot 3 free throws many, many, many times, we would expect him to make an average of 2.39 of his 3 free throws. That's really hard to say. 3 free throws. That was what the expected value would be. Y'all ready for the calculator? Okay, I'm going to use the Netflix data because it's boring when you only do 4 of them. So we're going to go to the next Netflix data. All right, so I'm going to go jump to my calculator. If I can find my calculator, there it is. All right, so we're going to be using the L1 and L2 again. So we're going to go to Stat and then Edit. And in L1, you are going to put the outcomes, so 0 through 5. And in L2, we are going to put the probability of it happening. So I'm going to do 0 through 5 here. Okay, and then put those probabilities in there, just as they're written here as the decimals. I'll give you all a second to get those done. I'll make this bigger. If you don't have the PowerPoint in front of you, you probably want to look at my numbers. All right, does anyone need another moment? So this is going to be really familiar what we're doing. We're just adding one tiny little bit. So go to stat and then go over to calc, and we're going to use one variable statistics. Your L1 is going to be your list. Your frequency list is going to be L2. So second 2 gives you L2. So your frequency list is L2 and your list is L1. And then go to calculate. And this gives you the mean of 1.49, which is exactly what we got. Does anyone need me to go back over that? So probably for the first year that I taught this, I did not know about this. Every time I teach this class, I learn something new. And I haven't yet learned something new about the calculator this class, but I'm sure I will. And as soon as I learn it, I will pass it on to you. All right, so I'm going to jump back to the PowerPoint. Okay. So let's talk about the standard deviation. So what I've decided this term is to not have you hand calculate the standard deviation of your discrete random variables. I've decided it is a big pain in the tuchus. I will do it, and you can watch me or do it along with me, but I'm not going to make you do it by hand. But I'm going to do it for like maybe the basketball because it's small. But what we do is we take each, it's very similar to regular standard deviation, but with no division. So you take each data value, you subtract the mean, you square it, then multiply it by the probability, and then you add them all together. Then take the square root. So let me show you. I'm going to do the basketball data because I don't want to do that other. See, this is the one I'm removing. So this right here, this has math errors on it. So let's ignore that one. It has math errors on it. But I want to do the basketball data, so I'm going to jump over there. All right. So let's do this together. Or you don't have to do it with me, actually. So for standard deviation, I'm going to do, I take the data value minus the mean, which was 2.39, correct? And then you square it and multiply it by the probability. Plus 1 minus 2.39, I'll square it, then multiply it by the probability. Plus 2 minus 2.39, square it, multiply it by the probability. Plus 3 minus 2.39, square it, multiply it by the probability. I'm going to put that in my calculator. 0 minus 2.39 squared times 0.01 plus 1 minus 2.39 squared 0.0 plus 2 minus 2.39 squared times 0.38 plus 3 minus 2.39 squared times 0.51. So I got a standard deviation, which would be sigma sub x, approximately 0.4979. Whoops, I didn't square root it. This is the squared. Now I need to take the square root. I forgot that part. So I'm going to take the square root of that. So I have my sigma sub x is approximately 0.7. Unless I mathed wrong. I'm going to real quick use my calculator and check it. Because sometimes typos happen. That's not what I got. Wait, I must have typoed in the calculator. 0.01, 0.10, 0.38, 0.51. What? It gave me a mean. Oh, I see what I did. Okay. Nope. Okay. Yeah, I got the same answer. So this is how you would hand calculate it. I'm not going to make you hand calculate it. I'm going to go back to my calculator. This number right here, the sigma x right here, is that standard deviation. So just use the one variable statistics. Don't bother doing the whole thing with your calculator. It's a big pain and typos happen. And so, I mean, don't try to do the whole mathing the whole thing out. Putting all of that math, think about if you had a data set of like 15 and you were trying to do them by hand. The probability of making a typo in your calculator doing 15 of these is pretty big. So use your calculator. One variable statistics. When you do your, I'm going to do the one variable statistics. L1 is your list and L2 is your frequency list. Questions? So what this standard deviation does for you, because I'm sure you're like, why the heck do I need this? It has the exact same meaning. I'm not going to do all of this with the, whoops, the other thing. It has the exact same meaning as any other standard deviation. It tells you, it gives you like values where you're something that would be unusual. So you can use that to determine, would it be unusual for somebody to go into the store and rent one movie? Is that unusual? Would it be unusual for where am I going to expect to find most of the data? So we don't use it a lot in this case, but we will be seeing it more and more as in other things as we move on. So it's useful just in the sense that we're learning how to calculate it more than learning how to interpret it. Because we're going to be using it later and this calculation is going to become important. But a casino might be like, hey, this guy just walked out. He won on every single hand based on what we know. I'm going to get off of the screen right now. Based on what we know, you know, based on our math, would it be unusual for this person to win all of this money without cheating? Or would it be unusual for him to make 3 of his free throws 10 times? All 3 of them. We need that standard deviation in order to help us to determine whether or not things are weird, more so than to determine where things are normal, if that makes any sense. So there's not going to be a ton of interpreting the standard deviation in your homework. It'll ask you to find it, but there's not going to be a whole lot of interpreting it. The expected value, yes, you will need to interpret that. That was my last slide. I told you it was a quick class. Are there any questions on what we've done tonight? I can still share again and do more math. Questions?
Yes. You said for computing the expected value,
Mhm.
the frequency is L2, but if we're doing the wait, sorry, computing the expected value. We flip the L1 and L2, so X is L1.
X is L1, and then your X is L1 and the probability is L2.
Probability is L2.
Right. So in your calculator, when you're doing one variable statistics, your list you're looking at is the L1 and the frequency list is L2.
Okay. Oh, okay.
Yeah, we don't flip them or anything. You'll get your standard deviation and your mean, both of them. None of the other things on that list will make a whole lot of sense or really have any meaning. I mean, it gives you like your median and all of that stuff, but it doesn't have a whole lot of meaning in this case. We don't ever use median or quartiles when it comes to expected value and these discrete random variables.
Okay. Okay.
Did you already Did you already clear out what was on your calculator on the variable stats?
Okay,
I just want to confirm what I got was the same as you did.
all right, let me share my screen again. Yep, here we go. There we go.
Yeah, I did something wrong. It's okay.
Do
Thanks.
you want me to show you the other screen? The lists? To make sure you
Sure.
get the same numbers? Okay.
Yeah, thank you.
Yeah, here's my screen. I'll make it bigger. Ooh, that made it really bigger. There you go.
Yeah, I have the same information. I don't know what happened.
Okay, so then when you go to stat and edit, uh-oh, that's not where I wanted to go. Stat and calc, one variable statistics. Your list should say L1 and your frequency list should be L2.
Oh, I don't have that there. What can I do to have the L2 there?
Do second and then the number 2.
Thank you.
You're welcome. That should get you there.
Got it. Yeah,
Will
thank you.
you calculate that real quickly?
Yep.
Yeah, thanks. Okay. Good,
So
good.
a standard deviation is 0.93
Mhm,
and then your mean is 1.49.
mhm.
All right. You
Thanks.
feeling okay? This is 6.1. You should
Mhm.
be able to complete the 6.1 homework based on what we've done tonight.
Okay.
And then we will do the rest of chapter 6 on Thursday.
Perfect. Thank you.
You're welcome.
Yeah.
And
feel better.
anything else for while we're being recorded? I'll turn the recording off in a second and then be open for other questions. Anything else while we're on recording? All right, I'm going to turn the recording part off.